Lesson 4.1, Equilibrium of a Rigid Body. The objectives: we're going to be able to identify support reactions, draw free body diagrams for 2D rigid bodies, apply the equations of equilibrium to solve for unknowns, and analyze the constraints of a structure to determine if it is statically determinate, improperly constrained, or unstable, or statically indeterminate. And then we're going to recognize two-force members. So here you can see there is like an engine hoist, just like roll out engine hoist. It's for pulling an engine or carrying around something heavy in a shop. And it's got this little hydraulic jack that's bolted in with a single bolt at the bottom and a single bolt at the top. And then this jib here, this horizontal piece, is connected with a single bolt here, so the whole thing can kind of pivot when you crank up and down on this hydraulic jack. And this black part actually can extend or slide into the red part, and so there's these different numbers along here. The farther out it is, the lower the capacity of the crane. So those capacities are, it says like, 1 ton, a ton and a half, 2 tons, et cetera, et cetera. Where do you think they got those numbers when they, make this thing? Somebody has to figure out, is the hoist strong enough, And that's really more of a strength of materials concept that you would take in a future course if you take strength of materials. But strength of materials uses statics to find all these forces. I mean, it's really crucial that you learn the statics so that you can actually then apply it in other areas of engineering. But the designers have to find what all the internal forces are, the internal moment and shear and axial force. You've done axial so far, but you haven't done shear and moment. To find out if this, if this jib is okay. Not only that, also to find out, is this hydraulic jack big enough? Which size bolts to use? And while we're not getting to all of those internal forces yet, we will in a few lessons. But right now we're going to be dealing with mainly just finding reaction values. So we could look at this jib right here and turn it into a free body. Okay, and I don't know if these dimensions are perfect. I kind of scaled it to a degree here just to give you an example. But if you've got an engine, like 500-pound engine sitting on here, you should now, by the end of this lesson, be able to apply the equations of equilibrium and find out what this reaction is here at RBY and what these reactions are here at RA, and that will tell you what's going on here at A and at B. And whatever that reaction is at B, that's actually going to be that compression forces in that strut. So that's a pretty important thing that could start answering these questions that the designers had. And the important thing is free bodies are absolutely, without a doubt, the way to solve these problems. Now, you've done free bodies of particles, and now we're talking about rigid bodies. The difference is that there are dimensions on it. There's more than one point, right? I mean, before it was always like, the ring all these cables are connected to, or some point that multiple cables or ropes or whatever connect to, and those all have axial tension and compression forces emanating out from them. So all of the forces were concurrent. And that's not really the case anymore. Here you can see that there are forces that are not concurrent with each other. Yeah, these two are, and that's great. But, RBY and RAY are not. They're parallel, and the 500 pounds for that matter. And so now, not only do we have some of forces in the X and Y for this 2D free body, but we can actually start also using some of moments about any point equal to 0. Okay, but to build these free bodies, remember the 3 rules that I teach about free body diagrams. You're going to keep the part that you're keeping, including all the force and geometry. So here, this free body of this thing up here bounded in the yellow box. I've got the 500-pound load coming down. I've got A here and B and the angle of that, and then the length of everything. So I've kept all the parts that I'm keeping. And then I'm getting rid of all the parts that I'm getting rid of. The rest of the structure down here is not on this free body. And then at the cut locations, put the internal force vectors that apply. So technically, I mean, I'm cutting through this chain, and so that's why this 500 pounds is there. And then this vector here, these three vectors are reaction vectors as far as this jib goes, but they're also really just the forces that are being transferred through those bolts into the rest of the structure. So the reactions for the jib actually become the applied forces for the rest of the frame. But regardless, when you make your cut, you cut through a bolt, you know that you're going to have two components of reaction. Here, this is a special case we'll talk about in these slides, why there's only just one there. So just to remember a little bit about equilibrium of a particle, this is what we had before. Again, everything was concurrent going through B. So we had sum of forces in the X and sum of forces in the Y. We didn't have sum of moments because there's really nothing that you can't use a moment equation here because all the forces are concurrent. So there's no net moment generated ever. So you can't, sum of moments equation is pointless. But for forces on a rigid body, you get that equation. That's actually helpful. These moment equations, I know you all hate moment, but moment is actually, the equations can get you there faster than force equations, because if you pick the right spot to some moments about, then you isolate unknowns. Like if I want to find RBY here, I could sum moments about A, and guess what's not going to generate moment about A? RAX and RAY. So they don't even enter into my equation because their perpendicular distance from A is 0 since they act through it, right? So there's no moment generated by them. So then there's just moment generated by RBY and the 500-pound force. So you can sum moments about A and get RBY. You could sum moments about B and get RAY because RAX, I believe, goes through B. And RAY and then the 500-pound force would be the only things generating moment about B if I sum moments about B. The point is you can always pick spots, and you can pick very strategic locations, and it'll make a lot of your unknown values just disappear temporarily from your equation. So you don't need to solve for them. You can isolate things. So it's extremely helpful. I should say, it is the moment about the z-axis. We have X going to the right maybe and Y going up. Z's coming out of the page right at you, like a 3D. And so the moments are about that axis, right? So if we say sum of moments about B, keep in mind we are talking about the moments of, sticking out of the page. So if like right-hand rule, stick the base of your hand, base of your palm right on point B on your computer monitor, and your thumb's pointing straight at your face. That's your z-axis. So for equilibrium of a 2D rigid particle, we have sum of forces in the X, sum of forces in the Y, and sum of moments about the z-axis of any of these points. That's 3 equations of equilibrium. So you can start to solve for 3 unknowns. Let's talk about some famous quotations about free body diagrams. I found these in a library somewhere. And it says, the first one says, it cannot be emphasized enough that the only way to successfully analyze a rigid body structure, or any static system for that matter, is to draw a proper free body diagram by hand and big enough to see and use. And that was from somebody who has passed statics previously. And then there's another quote I found that said free body diagrams are a waste of time. And that's from the person that took statics for the 5th time and was shooting for the 6th time. Okay, free body diagrams are your friends. Please draw them. Okay, let's talk a little bit about support reactions. We haven't had those before, really. At the other end of these cable systems, they were like tied to the wall. That's a support. We didn't really get into that too much because we were cutting through the cables and finding internal tension and compression. But now we're going to have to start thinking bigger picture and start thinking with these equilibrium of a rigid body systems that, we're going to have to start thinking about supports. So we have 3 very basic ones here. There's others too that are more complicated, but these, if you get these are pretty much most of what we're going to do. And I've drawn, these are just with my own graphics. If you look in your textbook, you're going to see them drawn like this or maybe a little bit differently. And if you look online, they'll draw them differently. In other textbooks, they'll draw them differently. I mean, there are variations, but you get the point. A roller support is like wheels, right? So here, this is like, like it's connected to this beam with a little pin, frictionless pin, so the beam can pivot about this point up here. But then this whole triangle is sitting on some skates, so it's like roller skates. It's sliding up and down this incline, and those are frictionless wheels. We always assume so. That only generates a force that is normal to the surface it's rolling on. So here, the reaction would look like that, pointing straight up. Well, not straight up, pointing straight towards the roller from the ground. The ground is pushing up against the wheels with that force R. If this incline is on this angle of theta, look what it does to the reaction vector. Theta is actually, if you have a slope given to you with an orientation of theta to the horizontal, the reaction vector is going to have that orientation of theta to the vertical. And that's because this vector is perpendicular to that line right there. So you have to draw it out, draw a little triangle. You'll see it. But don't make the mistake of misassigning this theta when you're calculating this R vector. This one over here is exactly the same thing, and I draw this one a lot just because it's easier to draw, especially by hand. You just draw a wheel underneath. Okay. Usually, I will say it kind of depends on the problem, but usually we even though we draw it this way, rollers, we often allow the vector it could be pointing up against the wheels if the ground is pushing against the wheels, like the wheels are pushing down, like you with roller skates on the ground. But also, if the structure is actually having a net pull, like it's pulling up and it wants to lift the skate up off the ground, in statics, we usually really mean for those wheels to actually be able to be held down against the ground. So meaning that if this rod here were in tension, this reaction vector could flip directions and point down. Sometimes that's not true. You have to look at the way the question's asked. Usually they'll say like it's just, something is just resting on the ground and it might tip over unless the force is maintained at a certain level and whatever. Then then it can lift off. But normally you can assume that these reactions work both ways, that they can actually push up or hold down the structure. All right, so a pin support. A pin support is like the roller that we had here, except for that instead of there being wheels, it is welded or bolted or whatever down to the ground. So it is fixed. So you get two components of reaction. You get an R sub y and an R sub x. Okay, so it's slightly more complex. Remember, the goal here is we've got to look at pictures and turn them into vectors, because statics is all about drawing your vectors and summing forces. So you have to be able to look at the picture and draw the vectors that are required. So here, just to go back, we found that you can get one reaction vector when you see a roller. You automatically know one reaction vector. If a lot of times the roller is on a horizontal surface, like flat Earth, then the reaction's pointing straight up. Over here at the pin support, we have two reaction vectors. Now, you might say, well, yeah, I mean, really, maybe the beam is pushing down like this against this pin. Wouldn't that be one, because then the pin's pushing that way? Yeah, you betcha that it is, but you don't know the orientation of that vector. It can be whatever it needs to be. And so we usually solve for them in terms of x and y, because it really helps when we do our equations of equilibrium. We do sum of forces in the x and sum of forces in the y. So we can solve for these two vectors individually. If you ever want to find like the total reaction, irrespective of orientation, you can just do the square root of the sum of the squares of these two values, and you'll get the total reaction vector. But that's actually quite rare that we get into that too much. You'll do that a little bit in strength of materials if you take that course, when you might want to size the bolt, make sure that the bolt that's in here, the pin, is strong enough. Then yeah, you'll want that absolute magnitude. But here, leaving it in R sub x and R sub y is good. So again, roller support, one reaction. Pin support, two reactions. Now, Now, fixed support, 3 reaction vectors. We get an Rx, an Ry, and then we also get a moment vector. So this is a moment reaction. This is like, a flagpole sticking in the ground, right? If you just set a flagpole on top of the ground and didn't like bury it and, dig a hole and bury a few feet of it, that would be, a taller flagpole, wouldn't it? That'd be cool. But when the wind blew or you leaned against it, what would happen? It would fall over. So we have to bury them. Now that takes work. I mean, somebody's got to dig a hole, and pour some concrete down there and stick the flagpole and make sure it's straight and wait for it to harden and all that. I mean, why do you think we go through all that trouble? We are getting this reaction vector. We are making this reaction vector generate. And then when you push against the flagpole or the wind blows the flag, the ground is cranking back against the applied loading. So, as a general rule, if a support prevents translation of a body in a given direction, then a force is developed on the body in the opposite direction. And similarly, if a support prevents rotation, a couple moment is exerted on the body in the opposite direction. So supports are all about stopping movement. If you're standing on the ground, the earth wants to pull you even deeper. It's just that the ground is stopping that translation. It's stopping you from moving closer, and the way it's doing that is by putting a force against you. So supports are those reactions, right? They are support reactions because they react against the forces that are applied to stop motion. And that is going to be either translation. When a force is applied, it stops translation. Or if a moment support reaction is applied, it's to stop rotation.